Hey everyone, welcome to my video on the solids of revolution. We're just getting started. This video is going to look at discs and washers, talk about those a bit. You will need these red and blue objects that you have at home as you look through this, but we'll get to shells. That'll be a different method a little bit later, but just as a start to the solids of revolution, we'll be looking at discs and washers. So the first thing we're going to do is this question one. Draw a skinny rectangle perpendicular to the line shown. Draw what it looks like rotated around the axis. So perpendicular, so that's going to be at a right angle, and just do your best with that part. So let me grab my pen here. Alright, so we're going to come in and do something like this. So just a kind of a skinny rectangle, something like that. You can shade it in if you want. But that's where we're looking at. And we're going to rotate it around this axis. So when I rotate it, what's going to happen? So this will come down here, get rotated right around that axis. So that's the idea. And you can, try to make these look 3D if you want, but the idea is that you're just going to get kind of this flat circle that's right here. So that's what it looks like when it's rotated around. It's just this flat, thin circle. Whatever the thickness of that rectangle was, that's how thick that circle is going to be. And usually you can think of this as maybe like a cylinder, or really flat cylinder, not very tall. But a lot of times what they'll call this is a disc. So this is like if you think of a CD or DVD, those discs that you put in, that's what they're thinking of, just this really thin circular disc that's right there. Question 2, what general formula could you use to find the volume of this rotated rectangle or this disc? So what we're going to try is just thinking about, all right, well, if I think about maybe the area of this circle right here, what would be the area of a circle? Well, the area is going to be pi r squared. So if we think of this height of our rectangle, let's go and call that r. Then the area of this is going to be pi r squared. So we'll get pi r squared for that area. And the thickness is whatever that is, so something small, right? And in this context, you might think of this as like a dx. If your line was maybe rotated so it was vertical, might be a dy, but this thickness is going to be just that small change in how wide that rectangle is. So we'll think of that as a dx, or possibly, like I said, if it was rotated 90 degrees, we could think of that as a dy. Alright, so that's going to be the volume, so I'll go ahead and put that down here. So of a slice, it's going to be that pi r squared is dx, or if it calls for it, dy. Alright, and then if we add all these rotated rectangles up across a region, what would I get for the volume of an object? So what we're trying to do there is basically just look at what happens as we add up a whole bunch of these guys. So if we add up a whole bunch of these guys, what's going to happen? Well, this is going to be right, an integral of this pi squared dx, or like I said, dy on that. So remember, adding up a bunch of small things over a whole area, that's what we're going to do with these integrals. There'll be some starting and stopping place, so some bounds a to b on those. But that's the general idea, is that we're going to add up all these small disks and then just see what the volume is total on those guys. All right. And you can see on this one, right, there's kind of that purple is kind of my sample disk that's right there. So If you want to take a look at your red object, you should be looking at a disk that's right in there. Now, when we drew this, I connected my rectangle to the line, right? But that wouldn't necessarily have to happen, right? I could have a rectangle that's not connected to the line, but still perpendicular. So let's go and see what happens with that. So if I go ahead and draw that in, we'll get rectangle say over here, and you'll gonna have to imagine that's rectangle. There's my rectangle right in there, and then that is gonna get rotated around this axis. So once again, we're gonna get this big outside circle here, goes around, and again, you can try to make that 3D if you want. But there's also this inside piece, right? This inside piece also gets rotated around that axis. So this also gets rotated around. And we get this idea right in there. That gets rotated around. So that's what we're looking at, is sort of this idea of this disc with a big hole in the middle. And you can think of maybe several things. This is like a donut that's maybe been stepped on flat or something like that. But a lot of times what they'll call these is a washer. So this one is generally called a disc. There's no hole. And this one is generally called a washer. After the hardware that you can get, those metal flat pieces with a hole in it. So that's the idea. This rectangle gets rotated around, gives us a volume. And then we can do the same thing, right? We can add up all these volumes to get the volume of our whole object. So what we'll do is try to come up with the formula again. So if I go from the line to the top, we'll again call that big R, just like with the discs. And then from the line to the bottom of that rectangle, this will be, say, little r. Then what I can do is find the area of this face minus the area of this little circle, the hole, and then just subtract those two. So we're going to get big R squared by little r squared. And then all of that is my area. And then I'm just going to multiply it by my thickness, so times this thickness, which is a dx or dy. So that gives me the total volume of this washer, and then we'll try to go in and add those up. So let's go and put those in here. So washer, so this is for disc. For a washer, we'll get this idea of volume pi big R squared minus pi little r squared times this dx, or in case of going sideways, dy. All right, and same thing here. You're just going to write that as an integral for those guys. All right, so there's our first kind of look at the difference between discs and washers and how that plays out. So let's go and take a look at a couple of examples. We'll probably just get through the discs in this one. We'll do the washers in another video. So the disc here that I have is this red one. The first question we're looking at is, what is the axis of rotation? So you can think of, this, trying to picture where's that axis of rotation going to be. You can kind of see there's right in here, and this parabola that's going from that side all the way over to this side. And you can kind of think of that as being rotated around, come down this way. So our axis looks like it's like right on the x-axis right here. So this is our axis of rotation right here. And usually we'll just put like this circular arrow to indicate that's what we're rotating around. Draw a sample rectangle, and then we're gonna just draw those kind of rotated around our axis. So I want to draw it, say maybe we'll put one here and rotate it around. That would be something like this. All right. And then what is the volume of a general sample slice? So we're going to want to put in like what is the R and that sort of stuff. So you can kind of see a cross section here. So you can take these, somebody calls them Christmas ornaments, but these volumes of revolution, you can take them apart, kind of look at it. There's my parabola sitting right in there. This is kind of my general slice that I've taken right out of there in purple. Let's go ahead and write a couple of these things down. So the volume of a general sample slice. So normally, what we said before for disks, is this is going to be pi r squared, and we have a vertical rectangle, so that thickness is a dx right there. And then what is the r? Well, the r in this case is just whatever this height happens to be right here. So we could call that y. But we're doing things with dx, right? So it might help to write it in terms of x. But we have an equation for this, so we can just write this negative x minus 3 squared plus 4 in place of that. So that is also a valid choice for r. So it's negative quantity x minus 3 squared plus 4. And we can use that in place of that r. So we'll go down and put that in. And again, it's because we're using dx, we want everything in terms of x. So pi minus that negative squared plus 4. And that whole thing is going to get squared right there. And then set up an integral. So this is going to be the same, basically the same thing, but inside an integral. And we need some bounds. So it looks like these rectangles are going to go from 1 all the way to 5, vary across there. So say from 1 to 5 is what we want to integrate. 1 to 5. So we have pi times this negative x minus squared plus 4. And then that whole thing gets squared with the dx. Right. And then you can, if you want to do it by hand, square this out. Then you'll have to square this, and it's just a big long polynomial with powers, so more tedious than it is hard or anything like that. But we're just going to be using either the calculator or Desmos to get these guys. So one trick I'll go ahead and show you on these, you've probably seen it in some of the other applications, but I can do like y1 equals this negative x minus 3 squared plus 4. That just confirms that's what that function looks like. And then in my integral, 1 to 5, I can actually use that I times y1 squared dx. And it will go ahead and square that whatever I called y1. You can do the same thing on a calculator with the TI-84 as well. So putting these functions in is, I think, a good idea. That way you're not dealing with, oh, my parentheses were off, or I didn't quite group everything correctly. Just makes that part a lot easier to deal with. So we get 107.23 for that value. So go ahead and put that in. So we get 107.23, 2 decimal places. That guy. All right. The next video, we'll be looking at the blue ones, dealing with washers and how that goes. They're not too much harder, but just a little bit different things you got to think about. But this is disks. Notice the disks are always connected to the axis you're rotated around, so you're not going to get any holes at any point on those guys. All right, if you got any questions, make sure you post those to the forum.